Good day, everyone. My name is Chukwuemeka. I'll be presenting integrated machine learning GIS technique for optimized setting of utility-scale solar photovoltaic system in Maricopa County. As we all know, the world energy demands keep increasing and the cost of energy is also rising. Because of this, it's important to look for better way to integrate clean and affordable power. One promising solution is solar photovoltaic energy. Solar power is growing rapidly because the technology is becoming cheaper and many countries now support renewable energy policy. But even though solar energy is a great option, choosing the wrong location for a solar farm can create problems. It can cause conflict with how land is used. It can harm the environment and the solar system may not perform well if it is placed in an unsuitable area. In the past, people used simple methods like drawing site or map by hand to decide where to put solar panel. This method relied too much on personal judgment and are not transparent or reliable. This is why modern tools are needed. One of these tools is GIS, which means Geographical Information System. GIS helps us work with large maps and data sets so we can understand the land better. When GIS is combined with MCDA, which means multi-criteria decision analysis, and a method called AHP, the analytic hierarchy process, we can make decisions in a more structured and fair way. The main issue in solar site selection is that many traditional studies rely only on expert judgment. This can be biased and may not work well in different regions. Many studies also do not check if the location they select can actually produce good solar energy. Some studies even ignore protected areas like wildlife zones and places where people live. Also, using only one type of data like land cover is not enough. We need different types of information to find the right place for solar farm. So there is a need for simple data-based and reliable method that uses GIS, AHP, and machine learning together. This study focuses on Maricopa County in south central Arizona, covering approximately 23,890 kilometers square. The region has a hot, arid climate with very high solar radiance value, making it suitable for solar power development. Most of the land lies below 600-meter elevation with gentle slope, less than 5 degrees, conditions that are favorable for large utility-scale solar installations. This study used 7 key spatial criteria, each selected for a specific purpose. Below is a simplified, clear explanation of the dataset. This dataset were processed and combined to generate a spatial layer for the suitable model, which are solar irradiance, GHI, how much sunlight the area receives, solar and elevation, whether the land is flat or steep, land use, land cover, what is on the land, water, forest, building, etc. Distance to transmission line, how close the area is to power line, distance to road for construction and maintenance access, protected area, land that cannot be used because of their environmental sensitive. Methodology. We use a combined approach that brings together mapping technologies, expert decision making, and machine learning to choose the best location for solar farm. We started by preparing 7 important map layers. These layers represent the key factors that affect solar suitability. The first is GHI, which means global horizontal irradiance, and simply tell us how much sunlight reaches the ground. We also include the slope and elevation of the land so we know whether the area is flat or steep. Then we use LULC, which stands for land use and land cover, to understand what exactly site on the land, whether it's building, vegetation, water, or open space. We added the distance to road and distance to transmission line because solar farm need easy access for construction and must be close to power line to reduce connection costs. Finally, we map exclusion zones such as protected area where solar development is not allowed. After preparing all this layer, we apply AHB, the analytic hierarchy process. This method helps us to give different level of importance or weight to each factor based on expert knowledge. It ensures that the expert judgment is part of the decision-making process. To reduce human bias and make the result more reliable, we also use machine learning. We tested two models, random forest and edgy boost, which stands for extreme gradient boosting. Both models perform extremely well with an accuracy score of 0.91, which shows strong predictive power. This also revealed that sunlight GHI and slope are the two most influential criteria for identifying the best solar site. Once we had the weight from both AHP and the machine learning model, we combined everything using a method called WLC, which stands for weight linear combination. This test merges all the information into one final suitable map. The result is a clear visual representation showing which locations are unsuitable, which are moderately suitable, and which small areas are more suitable for solar development. This combination method made the entire process more transparent and more data-driven and more accurate than relying on expert judgments. Our findings shows that 97.7% of the land in Maricopa County in Arizona is technically viable for solar installation. However, only 0.3% of the land fall into the most suitable category. Then 0.3% reflect location where all favorable factors, high solar radiance, flat terrains, good roads, access, and close proximity to transmission line comes together. Although the percentage is small, this area represents optimal condition for utility scale solar development. Energy potential. The study estimates that Maricopa County has an annual technical solar energy potential exceeding 25 terawatts per hour. We are talking about a very large amount of usable energy. Now, when we combine all the land classified as suitable and most suitable, we get an area of about 494 square kilometers. If this land is fully utilized for solar power, it could produce enough electricity to support around 2.3 million households. This is a huge number, and it shows the incredible potential that Arizona has for solar development. It means that the state could significantly boost its clean energy capacity to reduce dependency on traditional fossil fuel, lower carbon emission, and even supply power to neighboring regions. In simple terms, Maricopa County alone has enough high-quality solar land to power millions of homes every year. This reinforces why choosing the right location matters and why our combined GIS and AHP and machine learning approach is so valuable. It ensures that the best sites are identified accurately and responsibly maximize energy output while avoiding environmental or land use conflicts. By integrating GIS, AHP, and machine learning, this study provides a more transparent, accurate, and data-driven approach to solar site selection. The hybrid method balances expert knowledge with empirical evidence and ensures that siting decisions account for terrain, infrastructure, environment constraints, and energy potentials. The results show that suitable solar corridors tend to align with existing infrastructure, reduce land use conflict, and lowering grid connection costs. The framework is flexible and can adapt to other arid and semi-arid regions. It can be further improved by introducing economic, ecological, or policy-based layers. References used while conducting our studies. Thank you.